Welcome everyone to this week's Autonomy Talk. It's great to relaunch the series. And this week I'm very excited to have with us Professor Sehoon Ha, who is an assistant professor at Georgia Institute of Technology. Something about him. So he received his PhD in computer science from Georgia Tech. And before returning to Georgia Tech as a faculty, he was a research scientist at Google and Disney Research Pittsburgh. Now, his research lies at the intersection between computer graphics and robotics. Many of his works include physics-based animation, deep reinforcement learning, and computational robot design. As you have seen from the bio, he has published in exciting venues, and his work has been recognized by many different technical but also popular media. And today he's giving a talk on guided reinforcement learning to learn interactive motor skills. I'm very excited to hear more about it. And I give you the stage. And also feel free to ask questions during the talk by raising your hand or writing in the chat to make the talk interactive. Without further ado, thank you again for coming, and I'll give you the stage.
All right. Thanks for the kind introduction. Hey, I'm Sehoon, and I'm very pleasure. It's my pleasure to give a talk in this prestigious seminar series. As introduced here, I'm Sehoon, an assistant professor at Georgia Tech. My research area is at the intersection of the computer graphics, and character animation, and robotics. I have done a lot of projects on virtual character control, and these days I'm particularly interested in applying what I learned from the computer graphics community and apply to robotic platforms so that we can develop a more natural and effective robot controller. So now I would like to share a few nice projects from our research group. All right, this is me. Mostly, as you can see, these are some of the highlights of my previous projects. I'm mostly interested in control of things. It can be, I started to control some of the virtual humans in simulated world. But also I've been working on control of sometimes abstract system, sometimes game, and this day, of course, I'm highly interested in the robotic platforms. And then what I want to do, let me stop. Yeah. So I believe people has dreamed about an autonomous robot for a long time. Actually, it's been a really long. I mean, this is the Talos from the Greek mythology, and it's much early. It's like a BC 400, so it's like more than 2,000 years ago. Of course, I believe this is not the first robot we ever human imagined. I believe even earlier, when there's no, the recorded history, people would dream about some autonomous agent they can help them. Of course, these days we are more looking at tangible opportunities. You can imagine where I get those images, right? There are some little bit weird artifacts, but yes, we are. When I ask the GPT to think about the future of the human and the robots, then many of us are actually we are looking at nice future that humans assisting us can be just a life companion, or that's just some assistance in our kitchen. Then these are mostly about motivation. Then what about implementation? Well, one of the notable approach would be the Leonardo da Vinci, 15th century. Once again, this would not be the earliest approach, but actually the Leonardo da Vinci already created some of the nice mechanical knight, which can do some sit down and some of the upper arm motions, which are pretty impressive. I believe there are no actuation at the moment, but still, this mechanical device kind of may show the nice progress toward the automated robotic agent. Now we are living in the much more interesting era that we can really develop an algorithm for real-world robots. If you go to some exhibition, then you see that the digital robots from the agility robotics are doing some of the autonomous tasks in more, the more working pipeline setting. They move box here and there. So I believe we are living in really good time. This is time for test our imagination. Similarly, we also want to develop some nice robot that can do some real world tasks. For instance, a robot that can rearrange the real world object to clean things up. So yes, we want to develop intelligent assistant robot that can perceive surroundings and interact with them so that they can make our life much better. Since actually this is the long common example that I and my colleagues at Google are using, we want to have a robot dog at this level of intelligence. Here, the dog is fetching a beer by itself. You just recognize the surroundings, open the refrigerator using a leash, and then find the beer that which is the favorite of his or her master. I believe this dog does not use any external sensor or the privileged information. Just this dog is handling everything using his brain and his body. So by doing it, I hope that we can develop a nice robotic agent that can do some last mile delivery, or they can be lifelong companion of human, or even they can give some nice daily assistance for a disabled person.
Why are you coming upstairs, Eli?
Sorry?
I think there was it a question, Vince, or was it a mistake?
Sorry, didn't realize I wasn't.
Okay, no worries.
All right. Then probably many of you are familiar with the deep reinforcement learning, I believe. And deep reinforcement learning has been a popular approach for developing intelligent robots. Why? This is really basic stuff, but the DRF finds an optimal agent for the given sequential decision problem. We just formulate it as some maximization of the cumulative reward problem, and then we want to find an optimal agent. So here's an agent, and here's an environment. An agent take an action and then get some state, as well as the reward, which evaluates the quality of the effectiveness of the actions. And then agent make a decision based on this inside internal brain. Oftentimes we use the neural network. That's one of the key breakthroughs research community have made. Then this with the massive parallelization advances in a software engineering technique, then we can simulate thousands of the robots simultaneously, and we collect a massive amount of data within just a few minutes. By applying this, we can develop a nice locomotion controller. This is just my early work that used the real-world data to train nice, effective locomotion policy on hardware. And it will generalize to unseen situations. Recently, we can extend that approach for the more complicated task. For instance, the bipedal locomotion of the quadrupedal robot. So I'll say deep reinforcement learning is a nice automated tool for developing a motor controller for challenging tasks. But however, despite those recent success, deep reinforcement learning is slow because it leverages the expensive simulation. Simulation is expensive, and even worse, even with the expensive simulation, when it comes to certain objects, such as the deformable objects, they are not accurate. So that's the problem. To simulate those real-world materials, we need to make some simplifications, but they result in inaccurate simulation. In addition, they are less scalable. I would say the parallelization typically requires massive data exchange, and of course, still we can do some certain amount of the parallelization, but actually compared to just a fixed data imitation learning, deep reinforcement learning is less scalable, I would say. And they are also vulnerable to local minima because it always prefers the data near the current policy. If we are familiar with reinforcement learning, I would say they prefer on-policy data. So here's some illustration. Let us imagine a problem of learning a policy to manipulate bread. The state-of-the-art FEM will be expensive. This is from graphics community. They looks really, really nice, and they capture some of the natural phenomena. But unfortunately, this does not mean that is accurate. It will exactly reflect what will happen if we, approve those bread. And also, it's super expensive. See those amount of the finite elements. The simulation is super expensive. So we need always we want more samples. That would be the naive approach to make the convergence of deep reinforcement learning better. Just we collect a bunch of samples and stabilize a policy gradients. That's something we oftentimes approach, and many times it works. But my question is can we do better than just generating more and more and more samples? I'm in that sense, actually, I'm interested in the guiding the deep reinforcement learning. It can be either from the expert policy. I am highly interested in the bridging the model-based control community and the reinforcement learning community. I respect all the historical advancement made by a previous genius. And also I'm from graphics community, so actually I'm highly interested in getting some inspiration from the human motions. Of course, foundational model will be also interesting choice. They are making they really know something about the human knowledge, and then we believe we can leverage it for real world applications. So I classify our research project into these three groups, and let me just cover it one by one. By the way, just please feel free to interrupt me at any time.
The effectiveness of
All right.
through hardware experiments. Demonstrate.
Yeah, this is the one example of the our research group. Here you can see that this one actually shows the very periodic and the model. If you are familiar with the lag locomotion, then I would say this shows the very MPC-like gate. But in this work, actually our approach was a little different. We propose imitating fine-tuning strategy. We take the model predictive control and we bake that into a neural network policy using imitation learning, and then we fine-tune it using reinforcement learning. Why we need to do this? Because we want to take the style of the model predictive control, but also we want to improve the performance using reinforcement learning. From the perspective of the reinforcement learning, this kind of pre-training give us much better style rather than weird creative gate of the reinforcement learning. But as a result, this is the performance of the MPC controller in simulation. On the other hand, when it comes to the our approach, the IFM, we get much better controller while they enjoying the nice metric periodic gate of the MPC. And we believe this is actually the pretty generic philosophy. So we are working on migrating to hardware by taking that policy, model-based control policy, and fine-tuning for humanoid locomotion. This is in progress, and we hope that we can submit the work pretty soon. Similarly, how do we design the expert policy? Can we just do we really need to use the model-based control? No, here our hypothesis was that, we may be able to use just the previously learned policy on simpler tasks. So we hypothesized that a complex skill can be learned as the perturbed version of simpler skills. So, for instance, turning left can be viewed as the constraint perturbation of the working straight. Yep, and the reaching target can be perturbation of the working straight and the turn left, turn right. And based on this kind of the hierarchy, we can design a complex skill relation graph, and we use the previous skill as the a requirement for those interaction skills. Then we need to learn two policies. First one is the weight network that finds how we can weigh each of the skill library, as well as we also need a residual policy that corrects the composition of the existing skills a little bit. Then it results in the much faster learning while preserving the nice style of the original skill. In this case, the walking straight. We just focus on the tuning of the walk straight and then propagate the same style for more challenging motor skills. Then by doing it, we can do interactive navigation, such as pushing the object to the target position. Yeah, similarly, we can apply the similar approach to navigation. Here, our task is the outdoor navigation. Note that this is a little different from the typical navigation because we need to understand the semantics of the environment. Just we want to follow the road rather than going through the grass. And here we take the learning by cheating approach. We take the abstract teacher. We first train the teacher in effective teacher policy in the in simulated environment using privileged information. Once we have an effective teacher policy, we transfer it to the realistic simulation world using behavior cloning. There's no, we didn't apply the reinforcement learning based fine tuning here. We just got the kind of the satisfactory policy. And then we deploy it to real world using the to validate the learned behaviors. We take the 6 tracks on the in the Atlanta area. Each one is about the 0.4 to 0.67-ish kilometer, and then total was like 3.3 kilometer or something. Here's fast forward of the our navigation. They mostly work nicely. Sometimes we need a little bit of the intervention so that just to prevent further disasters. But just with a handful of the assistance, these robots were able to navigate pretty nicely. Of course, that does not mean that this policy was always successful. And I believe the actual research will be much healthier when entire community is transparent about failure. So we also want to share some of the beacons, the failure modes. Many times our semantic segmentation are not working great. Another interesting failure was sloppy driveways. Because of the driveways, we in our simulation we didn't have any data of the driveway. So every time they look at driveways, they get confused. First, the GPS drifting was one of the big failure mode. we believe it can be corrected using better SLAM techniques. But anyway, at the end, no robot was damaged seriously, just that this robot dog was tired a little bit at the end. And once we have the nice navigation policy, then we can use it for the assistance of the blind or the visual impaired person. This was the little early work that we published to the HRI late breaking report. This is kind of preliminary version. And here, the key is how we model the human-robot interactions. Oftentimes, people use just a rotating rigid rod, that assuming that the human is just simply following the given agent. On the other hand, sometimes we have the rigid harness handler that assumes that human always located at the fixed offset from the robot. Then human and robot rotate together, which is good, but in reality, there's more flexibility between the robot and human. So in the next version, we develop a concise mathematical model. We call it as the delayed harness to better capture human-robot interaction. Here, first, these are the initial locations of the human and robots. And then we proceed a robot first. And our assumption is that the human takes the action. This is probably the resting position for the user with the harness. But instead of going there directly, it takes some time to get there. So we get we move the human to some interpolated position because to model the expected delayed communication between a robot dog and the human. And we validate that using collected data. This will give us much better prediction. We also introduced some expert design safety predicate to prevent the filter out some risky actions that can either potentially damage a robot or, more importantly, human user. As a result, we were able to develop some nice robot guide dog that looks familiar with looks like a little bit like the real-world animal robot dog guide. They can do team navigation starting from this. This is our office building, and then they can, based on the human directional cue, they can safely navigate, guide the navigation of human handler. All right. Finally, I would like to mention a little progress toward the motion planning. So we also use the trajectory optimization as the guidance for developing nice autoregressive motion planner. So here the question is that, hey, we want to move our robot in home-like environment from position A to position B. Then how do we generate the corresponding robot joint trajectories? We use data and we train the mocap, the motion generator based on those trained data. So, for instance, starting from here, let's say we want to generate the robot motion that go up the stairs and turn left. Then this is the generated results by our autoregressive motion planner. All right, this is for the first chapter, and then I would like to move on to the next section. How do we use the motion capture data for generating the robot controllers? So this is my favorite work. Always I use as reference. So here this is the very popular work conducted by my favorite researcher, Jason Peng. He is now a professor at the SFU. And here that they developed the robot controller based on the dog motion capture data. And I believe But then my question was oh, wait, yes, of course, we can learn the robot dog motion controller from the real animal dog data. But we don't have that much of the dog mocap data. We have several open source the human mocap data, which has the the hundreds and thousands of motions, including such as the SFU or the CMU mocap database. Adobe also have one big one, I believe. There are many human mocap data, but I believe, as far as I know, in academia there's only one robot dog mocap repository. So for that reason, I thought, oh, it would be cool if we can directly learn from human motion data rather than just use dog data. So this is kind of the proof of concept work. Here, the motion is this is a teleoperation of the robot dog using the full body motion gesture. You can see that the human operator's motion is a little bit exaggerated. Sometimes there are a little bit of the manual command for transition, and robot dog's motion is a little bit wiggly at this moment. But we found that, oh, it's possible. We can learn the some of the control motions from the human motion. Then I would like to actually encourage you to think about how would you solve this problem if you are tasked to develop such controller. Then probably immediate thing you would do would be develop the motion retargeting network, as well as the a motion imitation controller that converts the retargeted motion into motor commands. That's exactly how we solve the problem. We retarget the human motion from the kinematic motion. There's some little more technique for making it more feasible, and then we train the physics-based controller that can track the retargeted motion and deploy to real world. That's it. This was the proof of concept. So by doing this, we can do some of the nice teleoperation. Here, the task is to push the box to the target location X marked. And actually, interesting thing is that this robot is walking, but it does not know it's walking. Just is trying to imitate the human motion, and as a result, it can walk forward. There's no particularly pre-trained walking controller. And because this is the teleoperation, just we can interleaving the pushing and the walking motion based on the operator's commands, and then we can achieve the task. All right, this is good. We show that this is possible. Then the question is oh, this is possible, but what's something we don't like? There are many things. The emotions are definitely motion quality is not so great. It takes many time to achieve the simple task, but more importantly, we didn't like the performance. Our very simple supervised learning based motion retargeting network. It only translates a few handful of the human motions, and its accuracy was not so great. So we decided to improve it in the next version. Here's our adversarial learning-based approach. Now we take the motion capture data, and then we retarget to the more robotic data using the nice adversarial technique. So here's an illustration of our method. First, we pre-train the motion prior. So basically, we pre-generate what robot can do, and we generate the compact command space Z, which is much lower dimensional than the original state space X, and then treat this as the embedded space. This gives us a nice conditioned problem. And then we use the adversarial learning. Here, the generator takes the human motion and outputs the latent space robot command Z. And then we want to make sure that the generate command is the it must be similar to the given robot data set. This is the model by the training a discriminator. And then there's also feature loss that the kind of the guides the high level correspondence, such as the root velocity. And this version starts to work much better. Here's the retarget motion of we retarget the human wall wiping motion, and onto 3 different robots. Here we have Spot, we have Daisy, and we have Stretch, and you can see that they all wipe the wall in their own ways. They're not particularly doing the same thing because due to their body dimensions, every robot has their own capability, but still they are trying to repeat the given task by themselves. All right, it looks great. Then is this really realistic? Can we deploy the given motion to real world? The answer is yes. We take the human sword fighting motion and deploy onto the robot, Spot robot, and then it was able to reproduce the same motion. First, here we are not doing anything useful, but we are very excited that our approach of the learning robot motion from the human starts to work better and better. We are very excited about this demo. And then we didn't like the existing requirements for the pre-generated robot motions. So we developed a new guided unsupervised reinforcement learning technique. Here, the key idea is design a cycle consistency reward. Basically, the human motion can be we must be able to reconstruct the given human motion from the simulated robot motion and vice versa. So we trained the two robot to human mapper and the human to robot mapper. Human motion must be able to reconstruct it, and the robot motion also must be able to reconstruct it from the human motion. So this was the our cycle consistency based reward design. And then without any pre-generated motion data, we were able to train a retarget variety of the motions, such as these. Note that the dancing, there's no particular manually designed things, just it tried to retarget the motion just like that, in that way. We can do more and more. Here are different motions. And then one nice thing about this approach is that this kind of approach is that we can always use the existing larger foundational model that is designed for human motions. For instance, we can use the text-to-human model to take the squat down and then jump, and then it generates the human motion first. And we used our approach to convert it, the corresponding human motion to robot motion. So from the simple text inputs, we can generate the corresponding robot motions. We don't need to retrain a bulky data, or we don't need to collect a large amount of the robot motion. Just we use the pre-existing foundational model. All right, then we want to apply it to something some little more complicated scenario. Now we are looking at the multi-character interaction. Here is a sparring motion of the two human characters. Can we apply the similar technology to this kind of the multi-character interaction scenario? The answer is yes. Here's a sparring motion of the two robot dogs. You can see that these motions are not exactly the same, but you can also see that observe that they still combines they express some semantic gist of those human motions. So here, the key research idea of the research project is that how do we extract the key idea from the from the given human motion. All right, then I would like to move on to the final section of our research, foundational model. So actually, I would like to start from one of my early work. This is, of course, not based on the foundational model, but there was some correspondence. So this is my one of the work I did during my PhD. So here we wanted to train the dynamic skill of the virtual human. And then here the key idea is that to leverage the guidance of the human. Every time it fails, then we give it some guidance, push fit against the reward, and we can then this virtual agent try to follow human instruction, and as a result, it can achieve highly agile motion. Look like this. Similarly, this is also not the foundational model, but the human preference can be actually leveraged to develop really nice controller. For instance, even for assistive devices such as exoskeleton, we take human feedback. Just the human decide whether, oh, I like this one better than the other. Just the A/B question, and from the A/B, we fine-tune the controller parameter of the exoskeleton. We have analogy of the kind of the Pandora music for exoskeleton controller. You just select a better controller, algorithm find the next candidate, and using a learned preference using the RankNet, and then we feed that the new proposal to controller. And we found that it can actually find the nicely optimized controller within a few iterations. So my point is that the human input is very useful when you develop a controller. And then these days, a large language model or the foundational model can be leveraged as the kind of proxy of the human insight. So, for instance, we can connect the language instruction and the policy learning by leveraging foundation models. First, we generate the language command, swing arms more, and then we generate GPT generates a prompt, generate the human motion using the pre-trained foundational model, and we target it for the robot. And by using this, we can, similar to the previous project, we can develop the nice humanoid motion from the language command. There are also the iterative refinement algorithm to make the learning faster. All right. Also, we can apply the we can apply the leverage the large language model for mobile manipulation. This is the work I did. My student did when he's doing internship at Meta. We developed the mobile manipulation controller, and actually it worked much nicely than we thought. It achieves almost 98% of success rate in unseen environments. And consider that this is the very long horizon task that we pre-train the basic controllers first, and then we learn higher level control policies, corrective network, and the coordination network to learn this long horizon task. But then this one worked nicely. It is robust against the perturbation. It just a bit because that is pre-trained, is nicely trained using reinforcement learning. Also, it's robust against the people. It tries to go to the navigation goal, and while human teasing it, it can go to the final location. Right. Also, the learned policy is much more robust against the object perturbation. It's not predefined, pre-programmed sequence of the navigation and object pickup. sometimes even in the middle of the object picker, it just cancel it and readjust its position. But my point is that if you have such a robust mobile manipulation policy, now you can easily connect to large language model. Here, we train the we connected the large language model, and from the library of skills, it generates the order commands. Then, from this kind of the high-level policy, high-level commands, language commands, it can execute the some home rearrangement task, which requires a multiple sequence of the work. So actually, this is interesting observation I have these days. The large language model is very fancy and quick way to write a paper. But do such a large language model research, you may want to have the well-developed a low-level controller so that you can take everything from the large language model. Here's the last work I would like to share. Here the task is the this is the object navigation task. So here that we want to find the given objects. Then it look around and finds the most promising direction and navigate to that direction. So here the key is how you generate the frontiers and evaluate the promise kind of the score of the those frontiers. If you see here, then but people would be able to tell that, oh, there's a little hallway, and then maybe at the end there will be a toilet. Yes, here the key idea is to leverage the visual language model. We compare the feature alignment between the given images and text prompts, such as oh, there will be a bed ahead. And then by comparing the cosine similarity between image and the text prompt, we can kind of get the very nice similarity, very nice guidance of the for object navigation. Right, that's pretty much it. We aim to develop intelligent robots that can make our life better. And we study optimization, deep learning, and interaction techniques. All right, that's pretty much it. Thanks for your attention. And let me know if you have any questions.
Thank you very much, Sehoon, for the great talk. Let's open the stage for questions. You can either type in the chat and I will read it for you, or you can raise your hand and directly ask. Up to you. Who wants to be the icebreaker? Okay, I'll be the icebreaker. So actually, you showed a lot of many interesting projects. So I will just sample some of the questions that came up. I actually want to go back to the very first thing you presented about compositional skills. And I wanted you to comment a bit on the limits for this compositional. So have you found, for instance, some bottlenecks on how many skills you can learn or how many compositions you can look at? I remember you had this slide where you had different the architecture, but it wasn't clear to me whether you fully you reached the entire complexity of what you could do.
That's a good question. Actually, that's kind of the most common question we present this work at any places. So for now, as you can see, it's like I would say handful. Like there are 10 skills there, and those skill graphs are manually designed. So I believe the for each controller, it may have the up to 10. I believe it's okay to have up to 10-ish the lower level skills, I would say, or the dependencies. I think is okay. We believe if we push the limit and design the skill set nicely, then we may be able to support 20 dependencies but
Mhm.
probably we suspect that it won't be scalable up to 100 unless we introduce something else.
Okay.
One limitation of our work is that this skill graph is actually kind of manually designed. We thought these are kind of the just given by user, but one direction we want to explore is that how can we automate the given the creation of such a skill graph? Maybe using some algorithm we can develop a more concise relation so that we can kind of cover up the limitation of the scalability.
Mhm. Thank you. Thank you very much. Then there is a question from Maximilian on the chat. How did you train the
Okay.
network for text to human motion generation? So was the training done for that
We just
particular part?
all right. That's we use the pre-existing network. I'm not sure which version exactly a student used. I don't remember. But at where is the work? Here, I believe I think that he used the motion GPT, I believe, but I heard that we discussed a couple of different versions, and probably motion GPT would be the version for this one, but not 100% sure.
Okay, and Maximilian is reacting with this thumbs
Yeah,
up.
thank you.
So that's a satisfactory answer. Any other question from the audience? Any live question? Okay, does it seem so? Maybe people need some time to digest the various projects and cool videos. You
Yeah,
you have
feel
your
free to
email
reach out to
written
me.
up.
Yeah.
Is your email
Yeah.
written up on some of your slides so that people
But I
can
think
reach
no,
out?
but I think you can just type my name, then you can see my website. There's
Okay,
email there.
fine.
Yes, and it's also my name, Sehoon Ha at gatech.edu, so should be memorable.
Thank you. Thank you again, Sehoon, for the great talk. I'm so happy that we managed to have you on this series, and good luck for the next steps. Hope to see many cool videos coming up soon.
Thank you. Thanks for the invitation, and I hope to see you at conference, maybe next year's ICRA at Atlanta.
Absolutely. Yeah, it will be in your hometown, right?